Good morning, and thank you for joining us for World Quantum Day. I'm Whitney Clavin, a science writer and press officer at Caltech. It's my pleasure to welcome you to Conversations on the Quantum World. The series is hosted by this Caltech Science Exchange and gives us a chance to hear from scientists and engineers who are working on the cutting edge of quantum research. I'm joined today by Fernando Brandao, who is the Bren Professor of Theoretical Physics at Caltech, and also the Director of Quantum Applications at the Amazon Web Services Center for Quantum Computing, which is located here on Caltech's campus. They're working on building useful quantum computers of the future. Fernando is here to break down the complex topic of quantum computers for us today. Fernando, thanks for being here.
Hi, Whitney. Hi, everyone. It's a pleasure to be here.
Okay, so first question is, let's start out with a definition of quantum computers. What are they? And how are they different from the laptops we use today?
So that's a good question. So to answer, let me just say very briefly how our laptops work on a fundamental level. So they use like binary logic, which means the building blocks is what we call a bit, and that's just a system, a physical system that can be either 0 or 1. The realization of this physical system in our modern computers is using a transistor, which is a device that can have two states, 0 or 1. In a computer, we have billions, in a supercomputer, even trillions of these transistors, of these bits. And then we break up a very complex action, right? For example, this video streaming that we are having here, this is really broken down into a long sequence of elementary operations on these bits, right? Which involve either 1 or 2 or 3 of these bits at a time. This we call like logical gates or gates on these bits. And then the computer is really about this, right? Breaking up complex tests into a sequence of very elementary operations on these bits. Now, the idea of a quantum computer, which, it started being discussed around 40 years ago. One of the pioneers was Richard Feynman, who was a professor here at Caltech. And he had some influential lecture here on campus where he set up this idea that maybe you can have new types of computation and new ways of doing computation. If at the building block you don't have a bit anymore, 0 or 1, but you have a quantum mechanical system that can have two different physical states. But because quantum mechanics, right, is richer, and you can have like what we call a quantum bit, or a qubit, which also have two states, 0 or 1, but you can also be in a superposition of these two states at the same time, right? And if you have many qubits, you can have entangled states of them, right? Which is this special quantum states that can happen there. And then the idea is to, really put to use these peculiar features of quantum mechanics, the physics of very small objects like electrons, atoms, photons, and so on, to try to do new forms of computation.
Okay, so from what you're saying, it sounds like quantum computers are going to be more powerful and faster. Can you explain that a little bit?
Sure. Yeah. So the motivation, again, I can mention, right, like this, the first time that I think the question was asked if quantum computers, we could have a new model of computing based on quantum mechanics that would be superior to the way we do computation today, was in this lecture from Richard Feynman, and his observation was the following. So quantum mechanics is a theory that is more than 100 years old, and is extremely effective, right, at explaining the physics of the microscopic world. But there is one feature of quantum mechanics. There's many interesting features, but one of them is that once we start to applying the rules of quantum mechanics to a growing physical system, to a system of many electrons or many photons and so on, this gets very hard computationally. So the cost of doing that computationally like grows what we call like in an exponential way in the number of particles, right, in the system that we have. So this was already known, for a long time, and then the insight of Richard Feynman was the following. So he said, we want to simulate, or we want to understand the physics of quantum mechanical systems when they grow, right? That's useful in many areas. We can probably we'll discuss later some of them. But this is a computationally hard problem, right, for our modern computers. So what if we create, a new type of computer, but where the building blocks, they're quantum mechanical itself, And then, this computer will probably be very good at this task, right, of simulating quantum physics or understanding quantum mechanical systems. So it's a little bit of a circular logic, right? But it's an idea that actually makes a lot of sense, and this is one like of the biggest uses that we think of quantum computation moving on, right? Is exactly to understand a much better way the microscopic world, right? The quantum mechanical worlds, and this is many scientists, of course, in physics, but in chemistry as well, in material science, in biophysics, in pharmaceutical research, they all have this a need of understanding, right, the physics of large molecules, of new materials, right, of high energy physics, and this is one way the quantum computers, right, once they can build, could really help. They can be really influential.
So, and to be clear, basically, because quantum physics is the language of nature, we're talking about simulating nature. Like, we can't, with regular computers, actually simulate nature if we're not behaving like nature. Is that right?
That's partially right, but there's an interesting nuance here, which is we can simulate all nature on our modern computers, on what we call classical computers, right? The computers we have today. But it's a matter of efficiency, right? We can do that, so they are universal in the sense. But there's this exponential cost in doing so if you want to simulate quantum systems in general. So even though if you have the time of the universe, you could do that. In practice, some problems are out of reach because it takes just too long to really simulate and understand them. And for those problems, quantum computer really can be a powerful tool, right, for making further progress.
Okay, well, that leads me to want to know a little bit more about the actual applications of quantum computers, because we've heard a lot of hype where people are saying, this is the revolution and it's already happening, but we know it's not really true. So tell us a little bit more about what the actual applications are. And,
right. Yeah. Great. Yeah, that's a great question. It's a very hard question too. And the honest answer is that we don't really know what these applications will be, right? So it's very hard to think about applications of a computer that doesn't exist yet, right? So really to have a scalable quantum computer that we think will be, will give benefit to society, this is really still a long-term journey. Probably at least 10 years, maybe 20 years, we don't know, right? It's hard to predict, but it's really a very hard scientific and engineering task, but worthwhile nonetheless. But we have some clues, and we have we know some we have some understanding of what we call like quantum algorithms, right? Is basically what would be the applications of quantum computers. So one big one is the simulation of physical systems that I mentioned to you, right? There is probably the most well-known and really what got the field started, I think, at least like got a lot of momentum for the fields, was a discovery by Peter Shor in 94. He studied here at Caltech, right, undergrad, and then he was a researcher at AT&T back then, and he basically found a very efficient quantum algorithm for factoring to a big integer. So factoring is just the inverse operation of multiplying, right? So when you want to factor a number, you want to find what are the prime numbers that when you multiply them together, you get the original number. So I give you 15, you say, oh, 5 times 3, that's easy. But if I give you a number with 2,000 digits, for example, then it's pretty hard to to find the prime factors. And actually, the best methods that we have, they take like a pretty much like exponential time. So for a 2,000 digit number, for example, it's out of reach to factor at all. And why do you care about this problem? Well, because all public crypto systems that we have today, right, everything that allows us to, for example, buy something online on the internet in a secure way, they are based on the fact that it's very hard to factor big integers. So what Peter Shor showed was that actually on a quantum computer, if you have a quantum computer big enough, you could do it very efficiently. So you could break all this, public key crypto system, right? So at that point, it became a problem almost of like national security, right? So for one country to have a quantum computer before the others. And there was started having a lot of investment, right, from government, and of course a lot of interest in academia. Now, until the quantum computer is built, maybe there is other public crypto systems that do a better job, and cannot be broken by quantum computers, right? So this is an open question. There is like good actually candidates for that. There's a lot of research on what we call like post-quantum cryptography, but that's probably still the most striking application of a quantum computer, right? It's like a extremely important problem, right? It's very well studied, and where quantum have this kind of exponential advantage, right, over the best classical methods. So you know, like in quantum algorithm research, many people complain, you know, progress is so slow, it's so hard to find applications. But I feel because we always compare against like this great success, right, of Shor's algorithm, right, and it's very hard to find something, you know, as impactful as that one. But I mentioned one before, simulation of quantum systems. That's probably, you know, still, as far as we know, will be the biggest area of impact of quantum computers. And there is other problems, right? So there is problems like, you know, people study potential applications of quantum computing to machine learning. There is some ways of speeding up some machine learning tests, but it's a smaller speed up. And then once taking into account, you know, the overheads to build a quantum computer that we'll discuss later, you know, it's unclear how big of advantages will give. The same thing for vast varieties of optimization problems that appears in many industries. There can be quantum speed ups, but they are smaller, and we have to see really if they will pay off, right? So it's so again, we don't know the answer yet, but I think there is good signs that it will be impactful, and I really think that, you know, the best is still to come, right? That once we have these quantum computers work, you'll be able to do so much exploration and investigation that we'll find new applications for it as well.
Okay, and then how long would you predict it's going to take before we actually have like bona fide working computers that can use Shor's algorithm and do these other material design applications?
That's also a very good question. It's a very hard question to answer. You know, I'm sure my answer will be wrong, right? Probably, but I'll try anyway. But before giving my answer, okay, so I would say, like, you know, I'll be very surprised if it's less than 10 years, right? I think there's a fair chance between 10 and 20 years, like we do it. It might be that, you know, we find some really big challenges and takes more than 20 years, right? So, or maybe there's something fundamental about the universe that we don't know yet, that we find out trying to build a quantum computer, which prevents us from building one. I don't think it's the case, right? If quantum mechanics is correct at all scales, we should be able to do it. And as far as we know, it is. But who knows, right? So this is really science, right? It's not just engineering. That's an important observation that we have to do about quantum computing. But why is such a hard problem, right? Let me try to explain this. And it's because we can create qubits, right? In the lab today, we have them. We can implement this, like, you know, these basic logic operations between them. It's called a quantum gate. And to get some of these applications working, we don't even need so many qubits. You know, if you have really hundreds to thousands of qubits, we could run these applications. But there's a very important catch. And the catch is we will need very good qubits, like very reliable qubits, and very reliable gates as well. You know, so you know, for these applications, we will need this, like, you know, building block operations like these gates, right? Which only have an error every, like, you know, million times we apply them, or every 1 billion times we apply them. Exactly because, you know, as in our classical computers, we want to have this very complicated task that we break up into a very long sequence of basic operations, right? So the price you pay, you need a very large number of these basic operations, and they have to be reliable. Otherwise, you know, error adds up, and then, you know, you don't get any useful answer in the end. So to get this, like, reliability on the quantum gates and on the qubits, this is very hard experimentally. So right now, you know, the state of the art is you can have gates which have an error every 100 times or every 200 times, right? And we need, you know, an error every 1 million times, 1 billion times, right? So it's like many orders of magnitudes that we have to solve. And this looks a bit demoralizing, maybe, right? And it would be, if not for one key idea in quantum computing, which also is used, you know, in like classically in modern technology, but is even more important in quantum computing, which is the idea of error correction and of quantum error correction. And the idea here is that even though you know, our physical qubits, the qubits in the lab, right, that you build, you know, and there's many ways of building them, right? We can discuss. We can use ions, we can use photons, we can use, like, you know, some very small electric circuits that you cool down to very low temperatures. They will be noise. You know, there is no hope of making them as good as a transistor, for example. A transistor is extremely reliable. Like, you know, you can make like hundreds of billions of operations and you'll be there. But we don't have a pathway for that quantum. But what we can do instead is use a lot of this noisier qubits, and then do some collective operations in them, and then they will form together one better, what we call logical qubit, right? The qubit where you do the logic in the end, And if you use more and more of these physical qubits, and if the physical error rate is sufficiently low, but not that crazy low, then you can make the accuracy of the logical qubit extremely high, and then you can run these operations. These complicated algorithms. But then you have this overhead, right? You need like more qubits, and you need them to be reliably enough. Only now they are becoming reliably enough that quantum error correction can work. And there's a lot of initial results in this direction, which is exciting. But you have to scale up the systems, right? So for example, for factoring, we expect to need something between maybe 1 million to 20 million qubits, right? Which are accurate, like with gates that only have an error every 1,000 times, maybe every few thousand times that they applied. And it should take a while to do that, right? You require a lot of advances in quantum physics to do that. It's very exciting, but it's not something that we'll do in the next few years.
Because it sounds like you're saying, in order for these qubits to work and to be able to monitor the errors, you need these helper qubits, right? These extra qubits. And that means more and more qubits. But the problem is that can lead to more errors. Is that right?
Well, yeah, you think so, right? But that's the beauty of quantum error correction, right? So you have these more qubits, and then you can say, oh, now you have all these qubits, they are all having errors at the same time, right? So how can this help? But it can help because as you mentioned, some of these extra qubits they add redundancy, right? So let me explain a classical error correction, because it's extremely simple to understand, and then it will help. So suppose you want to store 1 bit in a hard drive, that we do all the time, right? So like 0 or 1. But then if there's an error, 0 turns into a 1, the information is gone. There's nothing you can do. But now suppose that instead of just storing a 0 or 1, whenever you want to store a 0, you store 3 zeros there. And whenever you want to store a 1, you store 3 1s there. Then if one of these 3 bits is corrupted, right, then you're still okay, because the majority of them still tells you the right answer, right? So now if there was a probability of error, like it's called P, the probability of error is like P squared, right? Or order P squared. So there is a gain. And then you can keep adding more, and then you can keep gaining. It's called repetition codes. Quantum mechanics, you can do the same, right? So basically what you do, you start measuring some of these oscilla qubits. You try to detect errors on them, like errors on the logical qubit, and then you correct for these errors. And if you really engineer this in the right way, you can get a gain. And then you can get these very, very reliable collective qubits out of the physical qubits.
Okay. And recently I understand that Google had an achievement in error correction. Can you briefly explain what that was?
Yeah, so this was what I was mentioning, right? So quantum error correction has 2 challenges associated to it. One is that you require to scale up the number of physical qubits, because, right, you need to pay this overhead to get this very reliable logical qubits. This is one challenge. It's always hard to scale up, quantum systems, right? Because you have to control basically the microscopic world at a very with a high level of finesse. And another challenge is that error correction is not always effective. Quantum error correction is only effective if your building blocks, if your physical qubits, and if your physical gates, they are reliable enough. So it's called like a threshold. If you're below this threshold for the error rates, you're okay. If you're above this threshold, do not bother. Errors will only add up. And we are just crossing this threshold for error correction, like in the quantum system that we can build. These are around 0.5% for the probabilities of error of a gate, roughly, right? We are crossing this. So we're starting to get this regime where, when we enlarge the number of physical qubits, when we increase the number of physical qubits that we use for the error correction, we should see an increase, right, in the, in how our logical qubit perform, right? The logical qubit should become more reliable when we increase the number of physical qubits. Just now we start to see that. And there's many people doing, this kind of experiments. Only now we start, there's many signals you can get, right, if you're in the right track. And Google recently did one such experiment like this, and got some, indication that we are in the right regime of error correction. There's still improvements that have to be done to really be in the regime where scaling up will pay off, but it's a sign that we are on the right track, right? And it was an interesting experiment. Okay,
then tell us a little bit more about the landscape of all the different types of methods people are using for error correction. I know there are different methods, and that you're working on one yourself. You might be able to explain with AWS.
Sure. Yeah. So to talk about the different types of doing error of possibilities for error correction, I think it's good to talk about like all the different types different types of like physical systems that we can use to build a quantum computer, right? So it's a very like rich area in experimental physics, and there's a lot of progress in all these approaches. So for example, some people, they just use like ions or atoms, right? And then you store your qubits in two electronic states of the atom or the ion, right? And then you make this atom interacts, using, you manipulate the qubits, the electronic states, using lasers, right? So that's how, that's the knob that you have there to manipulate the information. And you can make them talk to each other. If it's an ion, it's the Coulomb interaction, right? If it's an atom, you have to basically excite them to some high excited level where they interact as well. And then there's, nice progress there. And there is some nice features where you can move them around. And then, doing so, you have access to some richer class of quantum error correction codes, for example. Then there's people that do photonics, right? So photons, they're extremely good carriers of quantum information in the sense that the information is there. They don't interact much with the environment, so it stays there, right? So it's very good if you want to transmit over, optical fiber some information. We know that, right? We use all the time. But for quantum, information is also true. Now people say, because they are so good, let's try to make computation with them as well. Then it's challenged to computation because they don't interact with each other, right, very strongly. But there is ways, that you can circumvent the challenge. And there's, companies and academic groups, they are trying to, push forward this, photonic way of doing quantum computation. But they have unique challenges, right? For example, once the information is there, it stays there. But of course, you can lose a photon, right? So it's called like erasure error, right? It happens a lot there. They just lose a photon. So then they adapt, the error correction scheme to tackle this like dominant source of errors, right? So in the end, the protocols that they have for error correction is pretty different than for, ions or atoms, right? And there's the system that, Google uses, IBM, many academic groups, and we are building at AWS as well, which is called superconducting qubits, right? And the idea there, they're very interesting. They, just think about electrical circuit, right? That we learn in school, right? Where you can have, some capacitance where you store like energy in some electric field, and you have some inductor, it stores energy in a magnetic field, right? And then if you build this, you can have some oscillating current going around, right? Now suppose you do this very, very, very small, and you do it with no resistance, like it's called a superconducting material, right? And then you cool down to extremely cold temperatures, like really, maybe like a tenth of Kelvin, right, which is this unit of temperature above the absolute zero temperature, right? So extremely cold. So you put them at the bottom of some dilution refrigerator. Then, quantum mechanics tells you that this electric current will be quantized. We have just like some fixed levels, right? Not like not any level as it can happen as we learn in school, right? So it's like quantum mechanics. And then you can use two of these levels to be your qubits. And then, this you kind of control using microwave pulses. This is all in microwave range. So there's, a lot of stuff that was developed classically is very useful here. And you can try to operate these qubits. And it's a nice qubit because, the properties are nice, right? You can do reliable gates. You can scale this up. You can just fab this thing, right, in a silicon substrate, for example. So there's a lot of the ways as people develop classic computers can be applied here. And that makes it an attractive option. So here, there is a standard way of doing so, error correction, which was done in this Google experiment, and other people have done also similar experiments. It's called surface code. It was developed by Alex Kitaev, who is a professor here at Caltech, like I think 25 years ago. And that's a viable approach to scaling quantum computer, and it's exciting. But we know the overheads will be high in that case, right? We know we'll need like 20 million qubits if you want to factor a number using surface code. And one exciting idea is if there is more efficient ways of doing error correction, right? Maybe, not using a qubit itself, maybe using some other quantum component. They have more levels, more than 2 levels. And this is one of the things we are doing internally at AWS. This the area called like bosonic error correction, where you basically use a quantum system of many levels, and you try to do error correction in a more efficient way. We are, towards working on our first experimental results there, and I'll be happy to talk more about them once they're ready. But I think it's an exciting direction as well in error correction.
Okay, we're very excited about that. And now let's like step back a little bit and tell me like what gets you up in the morning, what excites you the most about this type of work?
That's a good question, right? It varies. It depends on the day, right? Some days like just say, oh man, so much complexity, right? It's so difficult, like what I'm doing, my life. But most days they're good. And it's one thing that is really exciting is the community of people working in quantum computing, right? So really this, because it's such a hard problem, such a diverse problem, there is like, electrical engineers, right? There's chemists, there's of course physicists, right? Theoretical physicists, experimental physicists, mathematicians, right? Computer scientists. And you just like, get to interact and work with very interesting people, very smart people, right? And you're learning new things all the time. That's very exciting intellectually. I also, like fundamentally is really right that you can, there is something very unique about quantum computing, I think, which is, of course, quantum mechanics itself is a beautiful theory, right? And it's and even counterintuitive sometimes. So it's great that you can spend your time thinking about this. But of course, it's a 100-year-old theory, right? And most of modern physics is around quantum mechanics. So that's not special of quantum computing. But what I think is special about quantum computing is that, and even technology based on quantum mechanics, quantum computers are not the first thing, right? So, a transistor actually has to use quantum mechanics to work well, right? A laser uses quantum mechanics, NMR machine uses quantum mechanics. But all these technologies was about like, we understand quantum mechanics to tame the physics of the object at hand, like the molecule in NMR, for example. And we try to mitigate this weirdness of quantum mechanics, right? To make them work as we want them to work. And quantum computing is the opposite, right? Say, oh, let's take the most weird features of quantum mechanics and just amplify them, right? And just use them, to our benefits, right? Technologically. And I think this is really an interesting twist in the way of using quantum mechanics, which are just really probably just starting to understand how to do it. But I think it's very exciting thing, right? To research on.
Okay, great. And then we've got just 4 minutes before we switch to the Q&A. So I think people would like to know how you got involved in this field. Can you tell us a little bit about your background?
Sure. Yeah. So I'm originally from Brazil, and I started studying engineering in Brazil right when I went to college, because I like physics and math, and I enjoyed the first 2 years. Then then after the proper engineering started, I saw that I was more of a scientist, right, than an engineer. And then I was split. I didn't know if I wanted to study maybe physics, maybe computer science, right? And this was 20 years ago, and I was trying to find something that maybe combined both, which wasn't clear. And I had like a gap period, maybe 6 months before making the transition, right, where I could just explore things. And then I was looking online, and I found quantum computing, which seems so exciting. It was even earlier days than today, right? And even I found in particular, like I started reading like John Prescott, who is my colleague here at Caltech. He had some lecture notes which are extremely influential. He had already written them by then, 20 years ago, and I started reading them, and they're great, and I was hooked since. So, and then I did physics already, knowing that I wanted to do quantum computing. I did my master's in quantum computing, my PhD in quantum computing, and been working the area since then.
Okay, great. Well, we've got a lot of questions, so let's go ahead and go over to the questions. The first one is about AI. Will quantum computing have a big impact on the growing number of AI applications?
That's a great question. The answer is that we do not know. It's an active area of research. There's a few challenges in knowing this before we have the scalable quantum computers in our hands. So one is that AI is a very heuristic area, right? So it's very hard to prove stuff about AI, right? You try practice, and then you see if it works or not, right? And many of it work extremely well. And we cannot try, right? Because we don't have the quantum computers yet. So, a lot of quantum computing research today is done in a whiteboard with pencils, right? Like you try to prove mathematically something. And that's not typically how you do AI research. Of course, on some very hand-waving level, you can say, AI, right, is about having this neural network, right? Now you can have a richer neural network using like a quantum circuit, right? So this ought to help, but we don't know for sure yet. There's another application, another possible application where you just take an AI test and you try to speed up the algorithm running, the algorithms that you have to use to train the neural network or to do some classification task. There is proposed in these areas. At some point, people thought that maybe there was even exponential speedups there using quantum computers. Then people found better classical algorithms. Now there could be smaller speedups, but because of error correction, we have to see in practice if they would still pay off. But I think it's an interesting area for research for sure, and I do think people will continue to find there can still be this talk between like what is the best classical methods, what quantum computers can do, right? It's an interesting interaction, and this will continue to happen, I think.
Okay. Well, now we've got a couple practical questions. These are kind of similar, so I'm going to read these two questions. One is from John Clavin. He says, will we ever have quantum computers on a small scale, like a phone or a watch? And then we've got Ray Chung saying, what are the chances that quantum computers replace normal computers? So those are kind of similar. Can you help us understand that?
Yeah. As far as we know today, quantum computers, and even will be my expectation for the future, even if you find more of these quantum applications, they can be very important for society and for industry, right? But they would solve, when they are useful. They're useful when we have a problem which is intractable for our modern computers, right? Where it costs a lot of time, or a lot of energy, right, or a lot of cores to solve this problem. And then for some reason, quantum mechanics can help, which is not always the case, right? But for some particular problems, quantum mechanics can help, and then quantum computers will be impactful, right? So, and this kind of problem is not the problems that we at least today see on our day-to-day basis, right? When you use our phone or when you use our laptop, we are not really solving these problems typically, right? So that's why maybe there is no need for we ever having quantum computers in our laptop or on a smartphone. So there is this question of needs, right? Which, as far as we know, maybe there isn't. Maybe it's okay to have just some quantum computers as a supercomputer today, right? Somewhere there, and you can access via the cloud that computer, right? And you can use it whenever you want. So probably I would see like quantum computers as an evolution of like supercomputers from today. Then there's another interesting question is, okay, forget about if you want to do it. Could you ever do it, right? Could the physics ever evolve to be able to do it, right? Right now, you need this huge dilution refrigerator, right? You need all this kind of control. It's like a big experimental setup, right? If you want to scale this up, maybe, you need like hundreds of this dilution refrigerator, maybe thousands of them, right? How to one day have in your, your cell phone. I mean, the sky is the limit for innovation, right? But right now it's hard to see a path. Right now we see these will be big systems, and this will be like you need like a data center for them once they scale up. Right. So how to make them small to the level of like transistors, right? And modern computer technology that fits like in the cell phone. That's even a bigger challenge, right? That we haven't even started addressing, I think.
Right. I mean, I've seen the pictures. They're like these big chandeliers.
Exactly. And those are even like, maybe you can put 100 qubits there if you're lucky, right? If you need like 1 million qubits, right? You need like a lot of them connected, right? So these will be really very large experiments. Like, like comparing to the scale of LHC is not wrong. It's really, we're talking about really a very, very big physical experiment, right? Requiring probably, like thousands of people working over like, decades, right? So this is the same as LHC, right? And it even makes sense, right? Because we're really pushing physics to an extreme that hasn't been done, right? To extreme of like very complex systems that you have a very high level of control over them in the quantum scale, right? So it's of course about technology, but it's about science as well.
Okay. And just for clarity, the LHC is the Large Hadron Collider Particle Accelerator.
Exactly. Yeah, which is probably very different physics, right? Like they found the Higgs boson, for example, is about like understanding the elementary particles of the universe and the best models that we have about them. So it's very different physics, but I'm saying like the scale of the experiment and the scale of the resources required to achieve the goal, I think, maybe will be the same.
Okay. Now we've got some questions on cybersecurity. Here's one of them. Fully realized quantum computers will be able to break many of the widely used cybersecurity protocols in use today, as you were explaining. What is the solution to this problem? And I'm curious to this is going to relate to another question we have. Are we going to have protocols on our computers to stop this sort of thing? Would we be adding software to our computers? How are we going to block this?
Yeah, great question. Right, so indeed, because of Shor and variants of Shor's algorithm, most of the public crypto systems that we use today in practice, they'll be broken if you have a scalable quantum computer. So we need a solution to that, right? Now, this is an area called post-quantum cryptography, right? Because it's about doing cryptography in a post-quantum world, right? Once quantum computers are around, and it's a very active area of research, and there is candidates, right? So the protocol that we use today mostly is called RSA, and then the protocol is secure, assuming that factoring cannot be solved efficiently, right? So this is what Shor can break. But you can come up with other protocols for cryptography. This is called like public key cryptography, And it's the useful kind of cryptography because this allows us, to for example, do a secure transaction online, right? It doesn't have to be like just I talking to Whitney. I can talk to many other people in a secure way, like roughly. There is other ideas for doing, public key cryptography, not based on the hardness of factory, but based on the hardness of other computational problems, right? So like, for example, in some problems related to you have a lattice of points in space, and you want to compute, like properties of this lattice, stuff like this. And these are not known to be broken by a quantum computer. So that's like, a good candidate, right? And now people have to make this, efficient enough that we can implement in practice. There's a lot of work being done and progress. There is also the question, can really quantum computers not break them, or it's just that we haven't thought well enough, right? And there have been also, a few attempts, and they get close to a solution, but they haven't. So, so there'll be like this kind of, dialogue between quantum algorithms trying to break these systems and people coming up with clever systems that cannot be broken by quantum mechanics. Right now, there is good candidates for this post-quantum cryptography. There is challenges in implementing them and deploying them and making them secure practically, right, which is underway. So I think, if I had to guess, probably there'll be good solutions that can replace RSA, right, by the time quantum computers are built. But it's not a bulletproof solution, right? There's always this risk, right? So there's another approach, which I don't know if it will be deployed at a large scale because it's not a public key system, and because there's challenges, but it's interesting nonetheless because it's quantum. Is this idea of quantum cryptography, right? And the idea is to use these features of quantum mechanics like superposition and entanglement, but in a different way, to establish a secure communication channel between two people, right? So if I have an optical fiber between Whitney and I can send her photons, and we can make quantum measurements in a way that we can get a secure key that no one knows. And this cannot be broken. This is not based on computational assumptions. This is based on the laws of quantum mechanics, right? So there's people that study quantum cryptography. There's way of distributing quantum, like keys over satellites, for example, right, over free space. So it's an interesting area. And is a potential solution as well, right, to this problem caused by quantum computers. So there's two approaches: post-quantum cryptography and quantum cryptography. And I think probably by the time we have quantum computers working in a scalable way, we'll be able still to do cryptography. Yeah.
Okay, good. And since you mentioned entanglement, we haven't really defined that. So here's a question related to entanglement from Stanley Dawson. What is the role of entanglement in quantum computing? And so I'd say first kind of explain what entanglement is, and then what I understand, it's the information in a qubit system becomes spread out through entanglement and shared.
Right, exactly. So entanglement is about correlations, right? So correlations, it's something that we understand well, we see all the time, right? So we can have two systems, like the weather on 2 consecutive days. Will be correlated, right? If it's raining the first day, it's like a higher chance of raining the second one, right? If it's sunny one day, it's a higher chance of being sunny the other day. They're not perfectly correlated, but they are correlated, right? Or two stocks in the stock markets of similar companies, right? Of similar kind of sector, they'll be correlated, and so on, right? So quantum systems, you have like, two photons, right? They can be correlated as well. But an interesting thing of quantum mechanics is that there can be stronger correlations that we have classically. So they can be correlated in a way that, we cannot explain this correlation just by some kind of like classical correlations that we can explain the weather, right, or stock markets. This is called entanglement. You can have entanglement of many particles as well. And entanglement, this gets subtle, but entanglement is one of the reasons why it's so hard to simulate quantum systems classically, because they have this very strong correlations. It becomes computationally hard to simulate them classically, right, with now modern computers. So, if you want a quantum computation, which is hard, it's always, there's nuances, but if you want to have like a advantage using quantum computer, then you will be required to, throughout the computation, to have states which are very entangled, right? There is a lot of entanglement there. And even for error correction in the quantum case actually can only work because of entanglement. Only because of entanglement, what you're saying, Whitney, you kind of delocalize the information using these entanglements, and then even though each part is being corrupted by the environment and there is noise, you can still protect, right? You can still protect this kind of collective information because they're entangled in the right way.
Okay. And now I've got a question about the number of qubits that you guys have been successful with. So this is from Ted Williams. So far, how many logical qubits have been demonstrated together in a single system at the AWS Center at Caltech? Now, I don't know if this is secret, you can't tell us yet, but I also, when you answer this question, it'd be good to know, like, what is the current maximum that people have been able to make a quantum computer with in terms of the number of qubits?
Right, that's a good question. So we it's not we haven't, we're still building our experiments, right, so towards logical qubits. So we haven't announced that yet. So what we're doing at AWS, I cannot tell much yet, but we're hoping to announce in the near future. But about logical qubits, it's not like a 0 versus 1 type of question, right? So it's really about building a logical qubit and think about what is the logical probabilities of error, right? So in the long term, we want to build a logical qubits for which the logical probabilities of error is like 1 in a billion or 1 in a trillion, right? Like extremely small, right? That's the challenge. That's the goal. Right now, right, because of this like kind of threshold that I mentioned of error correction, if you try a few years ago to be the logical qubit, we could, but because the physical components, the basic components are not good enough, error would just add up. Error correction will not help at all. So now we are crossing this threshold. It's not the goal. When people say I built a logical qubit today, just needs a logical qubit. I mean, in this, like Google make a good step, but this has not been accomplished like in a definitive way. We just want to have a logical qubit for which the performance of the logical qubit is a little bit better than of the physical components. That's the first challenge. It's called break-even for error correction. We want to cross this break-even challenge. Then cross it. Eventually we want to have where the logical performance is 100 times better, then 1,000 times better, then 1,000,000 times better, right? So this will take like many years too. And today, people are just trying to cross this first break-even point, where there are experiments with error correction with like a few qubits, 7 qubits, 9 qubits, all the way to like 49 qubits, which was this recent Google experiment, right? So that's the largest number of physical qubits. This is all about creating one logical qubit, but the performance of the logical qubit is just barely better, or not even that, than on the physical components. In the next few years will be the challenge of really getting the performance that we need out of them, right? So this is, this is a challenge that will take longer.
So the total number of qubits, what's the highest number of qubits, if we're just not talking about logical, but just physical, that people have been able to get to work in a quantum computer? Yeah,
that's also a good question, and it's nuanced, right? Because if you just, there's two things about number of qubits and how good the qubits are, right? So you have to talk about them right together.
Okay.
So for example, if you just want a qubit, and you don't mind doing just very limited set of operations and then being pretty noisy, there is a system with like 5,000 qubits, right? Like D-Wave, which is a quantum computing company, they have built them. But the control there is very limited, right? And there is like substantial noise there. If you want this kind of like where you can do gates in a universal way, which you can potentially build a quantum computer out of them, we are on like 50-ish, 70 qubits. Around 70, I think, right now is the state of the art. So,
okay.
Well, actually, no. This is with the surface code connectivity. If you just you can do gates, but with a kind of a worse connectivity, then like IBM, for example, I think they announced 400 qubits, right? So we are at this scale. But there's a lot of trade-offs, right? There's the connectivity, there's the quality of the gates, right? There's the quality of the qubits, right? So this is really the game that's not just one metric. There's many metrics that matter.
Well, okay. But then how many do you ultimately want to have a working quantum computer? What's the goal?
I think to get these impactful applications, and the more the better, then you unlock more applications, but it's around like 100,000 to 1 million. That's what we require to get the first interesting application. So
we're ways away.
It would take a while, but we'll get there, I hope.
Okay, and that leads me to what I think will be the final question, which is, what advice do you have for a college student trying to get into the quantum computing field? So this will be someone that will hopefully figure out how to get 100,000 qubits working.
Exactly, and we need them, to help us. Well, I mean, there's so much information online these days, right? So start like just like reading about the area. It's a very accessible area in the sense of like people say, maybe it's so hard to start learning about it. It's not like it's if if you come from computer science, there is like interesting sources tailored to computer science people. If you come from physics, the same. If you come from engineering, from math, so just start reading about that. Start learning. and then it happens organically, I think, right? That's, the more you read about it, the more interested you are, and then you learn more. If there is a way to talk to someone, right, in the area, always helps, right, to get some guidance on what to find. I think even Caltech has some good sources now, right, for in the quantum exchange, I think, that you could try out. So I think, yeah, today maybe the problem is that there's so much information, you have to know how to filter them, right? But then maybe getting, help from someone in the field. You can always write to someone, right? The person can guide you. I get some of these emails. I reply to them whenever I can. So it's I think it's a pretty big community by now. So there's many ways, I think, to engage.
All right. Well, thank you very much. We're going to wrap things up. Thank you so much, Fernando, for being here.
It's been a pleasure. Thank you.
And thanks to everyone for joining us. Next up in our conversation series, we have conversations on artificial intelligence. Hear from computer vision experts about using AI for wildlife conservation. And you can learn more about the bizarre world of quantum physics, including superposition entanglement and all that, on the Caltech Science Exchange. Find it at scienceexchange.caltech.edu. Thanks for joining.